So welcome to the day three, guys. Quite in a rush. Still new to this, so working on it. Today the job search is still going on. As you can see in my upper tabs, the work is still going on. We ask countless referrals from countless people, get no replies, direct application, leads to rejection, ATS friendly resume, whatever. Let's start with the problem. Cousins in binary tree 2. Given the root of a binary tree, replace the value of each node in the tree with the sum of all its cousin values. So we have a tree and we have to replace the value of each node in the tree with the sum of all its cousin values. Two nodes of a binary tree are cousin if they have the same depth with different parents. Okay. Return the root of the modified tree. Note that the depth of a node is the number of edges in the path from the root node to it. Okay. So if it's the case, we have 1, 2. So the depth of node 1 is 2, and for 4 it's 1, and for 5 it's 0. Okay, what is a cousin in a binary tree? So for 5, the summation value, whatever we say, sum of all its cousin value is 0. For 4, the sum of cousin value is 0. For 9, the sum of cousin value is 0. But for 1, the sum of the cousin value is 7. Let's see why. Because 1 is a child node of 4, and the sibling of 4 is 9, and the children of 9 is 7. So we replace the value of 1 with 7. Similarly, for 10, the parent node is 4, and the sibling of 4 is 9, and we replace the value of 10 with the children of 9, that is 7. Now comes to 7, the value is replaced to 11. Why? Because the 9 sibling is 4, and we replace the value of 7 with the summation of children nodes of the 4. Child of 4 or children of 4. So the 7 is replaced with 11. Okay, now let's take this problem to our board. Okay, we have this node, this node, and we have this and this, and we can say we have two more nodes here, right? Okay, there's one node, we can make it two. Okay. So for each node, I have to replace the value of this node with the sum of I have to replace the value of this node with the sum of these two nodes that are its cousin. So which node will be its cousin? So this is its parent. This node parent is this, and its sibling is this. But the grandparent of this node is this top root node. So for any cousin in a family also, or would mean in this particular problem, the grandparent node is same for cousin. So grandparent node is same for every cousin node. Okay, and the parent nodes are different for cousin. Okay, we have grandparent and then we have parents. So for a node, if the grandparent node does not exist, then the summation value would automatically become 0. As you can see in this case, we have 5. Since there is no grandparent node, the value is 0. For 4 and 9, there is no grandparent node, so the value is 0. But when the problem boils down to 1, the grandparent value exists. So, okay, sir, grandparent value exists. So we take the value of the grandparent and find the other children it has, and then sum the children node of that other parent and then replace the value here. Okay, what if we have a bigger tree? Let's say we have a more big tree. This was a small tree, we can have a bigger tree, right? We have this, we have this, do this, do this, and let's have more children here. Okay, so okay, for this particular node, what is the grandparent node? This is the grandparent. Okay, which is the parent, this is the parent, and which is the cousin of this particular node? this is the cousin node, right? Yes, this is the cousin node. So we shall replace this value with this, the sum of these values. Given the root of a binary tree, replace the value of each node in the tree with the sum of all its cousin values. Two nodes of a binary tree are cousin if they have the same depth with different parent. So same depth with different parent. So this is 0 depth, this is 1, this is 2, and this is 3. So if what is it saying? Two nodes of a binary tree are cousin if they have the same depth with different parent. Okay, so I was thinking that we can just pick these two nodes, but it turns out to be false because we have to pick this whole level because these all nodes are at same depth, and from here onwards all these nodes have different parents, right? All these nodes have different parents. So the grandparent and parent approach that I was thinking would fail here because for this particular scenario, then I have to check for the great grandparent, and our tree can be increasing further, right? We can have more nodes and in a similar way. So I can just keep backtracking and finding new parents and grandparents relation. So this approach that of a grandparent and parent we were thinking will fail because we need to find not just these nodes, we have to find all the nodes that are on same level but are having different parents than the original parent that we have. Okay, so for that particular case, if we take here, we have these two nodes. Okay, just a little different color. We have these three nodes, these two nodes. These two nodes have the same parent, right? And the rest of the nodes here are having different parents. Okay, but all these nodes are on the same level, that is level 3, right? And to these nodes the value would be same because these are the cousin nodes, and the summation of these cousin nodes, let's say for some, we will put these value in this node and also in this node, right? And whatever the sum of these two nodes is there, yes, this is 1, this is 10, this is 7. I replace 7 here and 11 here, right? So the if I find the level sum of this particular level, let's say it is 18 for the case in the, as per the example, the sum is 18, right? 1 plus 10, 11, 7, 18, right? We have 18 total sum, total level sum. Third level sum is 18. Now 1 and 10, 1 and 10 we have, and total sum is 18, right? So I find the sum of these two nodes, that is 11, and then I subtract this sum and replace the value, so it becomes 7. So for each node here, like for say this node we are considering for this case, so I will find the sum of the nodes that are having the same parents. So if I say, let's take some text. If, okay, so the size is quite small, font size extra large. So if we have level sum and we find the sum, the nodes with same parents, and then subtract the sum with the level sum, we will be having the sum of the cousin nodes. right? We would be having the sum of current cousin nodes, because for this particular case, let's just say for this particular case we have, for this node, these two nodes, these are the cousin nodes, right? And sorry, these are the cousin nodes, right? So if I have the level sum and I remove the sum of these two sibling nodes, then I will just easily get the values of the cousin sum, and then I can replace it here, right? Okay, so now I have to calculate the level sum first. So for the level sum, I can do a basic level order traversal. So a level order traversal, and for each level I will store the sum. So for the zero level I will store the sum, and then so on. Now the particular problem that arises is for this sibling sum. How I would find the sibling sum? If I am standing at a particular node, if I am standing, okay, this, let's just draw a new tree. We have this. Okay, so for this node, I want to know who is the sibling of this. I can have a parent-child relationship graph or map. We can say that this is the parent, and for each node, I will find the parent and all its children apart from that. Or we can just store the parent and the two children it has. For each parent, I can store that the left child is this x and the y child is y. And every time I'm standing at a particular node, I can just fetch the parent value. How would I fetch the parent value? I will have to pass the parent value, and then I will fetch the parent. Then I will check for the value, but it could be a case where both the values are same. So we'll make a issue, right? Okay. To just store the left and right of a particular parent and have to check it. You can just pass right now. For every node, I will just pass, since this is a parent. So when I will push this particular node that is a left right child of this parent in the queue, I will just push that this is the parent, and since it's a right child, I will push R with it, that this is the parent and this is a right child, and you are the node. Okay, and similarly for the parent, it will map it. It's becoming quite complex. Is there another way to around this? For each node, I want to know the sibling sum. So if I am a parent node, I know the children node, right? So if I am a parent node, I will know what children are mine, right? I'm a parent, I will know which child is mine. So if I'm a parent node, I know my child, that these two kids are mine. I will just sum them. That is, let's say that is S, and I will do level order traversal previous to this. So I will store the sum of each level previous. So firstly one traversal to store the sum. Okay. Then again start a traversal from the root node. Root node does not have any parent, so the sum is zero. But root node does know that these two are my child, and it will sum these two values, and this would be the sibling sum of its kids. Okay, and since I have already calculated the level sum in my array, the level sum, I know that this is the first level, and we know that the sum is stored at the first level, so I can minus the sum. So it would be just simple. Sum sum at level 1 minus sibling sum, and similarly for each parent I know the sibling sum, and I also know the level sum. So when I'm standing at this parent, then only I will calculate the sibling sum and replace the value of the sibling sum. Okay, so in that manner I can have the sum. So for this particular case I will have to do two BFS or one BFS, one DFS. Well, DFS will not work well with this particular problem because we have to go level by level, right? To say DFS will can also solve this problem. It's not like we can't solve this with DFS, but I think since we are working level by level, it is better to work with BFS. We can just go depth by depth. So when I reach the depth, I know the children of this particular node. I find the sum, sibling sum, and I also know the level sum from my array. I subtract that, replace the value of the children, push them in the queue, and similarly for this node, I also know the value of these two nodes and the level, and I can do that. So two VFS, right? Okay. So let's try to code this, and while we are coding this, you can see if it works or not. So first thing first for this QUEUE, sometimes get confused with the spelling of Q. Same goes for the map, unordered map spelling. Happens with me. Don't know for others. Okay. Q dot push root. I'm just doing a simple level order traversal, nothing else. Okay. Now to store the sum, I can have a vector, right? For each level, it will store the sum. Vector int level sum, we can call it level sum, and yes, just name it level sum. And while Q. Initially, I was planning to record this video in the day, but at the work or at the internship that I'm currently working at, my whole day was spent, so I was not able to record this video. Well, not a issue, right? I'm looking for some Discord server where people can refer me for jobs. Not able to find one. I'm currently asking referrals at Neetcode and LinkedIn and cold email, but it doesn't work that well. People don't reply that much, and I know that there are reasons for that. Don't want to reply to some stranger that just pops into your DM, right? You have int q size while n minus minus. We will pop the tree node that is on as current, right? And this q dot front. I'm thinking of completing the tree today, and after completing the tree, I have revised my graph concepts. So I'm planning to do graph for 3 to 4 videos. I will first pick up a topic of a graph, and while I pick the topic, I will first implement the topic, explain it, and then work on the problems of that particular topic. Okay, so I'm currently pop the node, so I will need to store this sum, right? Sum, we can just call it, right? For sum 0. Okay, so the sum plus is equal to cur dash val. I don't know what will happen, but just keep going. We have current sum, we have added the value to the current val. Now what I need to do is check for the left and right? If not, cur dash left exists, and you just need to do is q dot push cur dash left, and if cur dash right exists, q dot push. In India especially, I think getting a referral is very difficult because there are new platforms like TopMate and these kind of platforms. So nowadays you have to pay for the referrals. So getting a referral has become more difficult in India, especially. So this is the current experience that I'm having. Every day is a new job search. I'm using Well Found and these kind of platform for job searching. But yeah, well, any company that you work for Well Found or you just find out on Well Found, the first thing they give you is a assessment to work on, and that takes around 2 to 3 days to work, and that's a good thing. I mean to say they are checking the development skills, but after that, when they don't reply or expect that the server is the site that you have created or the code you have worked on should be hosted on some paid servers, then that doesn't seem that well because the payment is not that huge and you have to pay for the servers as well. So that doesn't fit well. But what can be done? If current left and then this, okay, so after this the loop is over. And what was the name of the vector again? Level sum, right? Level sum dot push back curve sum, right? Okay. So what is this? Just comment this. This traversal allows us to store the level by level sum. Okay. So this is our basic level order traversal that will allow us to store level by level sum. Okay, that works well for me. Now what I need to do is again do a BFS, and this time the BFS is to be started. Shall I start my BFS from the child nodes of the root node? Start initially push 4 and 5 in the queue. Will it work well, or should I start from the 5 itself? Let's start with 5 itself. Q dot push root again. Okay, after pushing the Q dash root, what I need to do, when I will come here, I will be getting the sibling sum of 4 and 9, right? So I have to pre-assign the value of root. I already know that the root value would be 0. So assign root value as 0. Now while not q dot empty. Now while not q dot empty, again I have to take all that particular part, that is int n is equal to q dot size, and then what I will do is while n minus minus, take the tree node that is current, then just pop the q front. Okay, okay, q dot pop. Now since I have popped this node out of my queue and I'm standing at this current, I can find the sibling sum, right? So int sib sum is equal to, if the current left does not exist or current right does not exist, we have to add 0, right? So for that case I have to write current dash left is not equal to null, right? If not equal to null, then current left dash well, else add 0, and shift sum plus is equal to current dash right not equal to null, then current right or 0, right? Okay, so now having the sibling sum of these two nodes. Now since I am having the sibling sum of these two nodes, what I can do is find the level sum. So I'm finding the labels on these two nodes. So index, I need to know the index of these two nodes. So where should I assign the index? Should I assign here every time I go? I start index I is equal to 1 from here. Every time I go, I will just increase the index plus plus every time, right? Uh, this is called as int I is equal to 1, and every time I will go, I will just increase it. Okay, I is equal to 1 sibling sum, and I've already got that. Now, if currents left exist, then do one thing, that is first thing first, that is current left val needs to be changed, that is level sum bracket I is equal to, no, level sum I minus sib sum. Okay, and q dot push current left. Okay, now I need to do same for the right child. If current right exists, current right val would become level sum minus sib sum, and q dot push. What I need to push is current right. Okay, so, and after doing so, I have to come out of the while loop and increase my I, right? I have increased my I, and I have to just return the root. Let's try to run this code. There is no compilation error. Okay, so we are getting wrong answer, and in this case we are getting right answer, that is 312. Okay, so it's 000, but why we are getting 32266 when it should be 77? Is the case 549, and the value it's assigning is 2. Okay, so why it's assigning value 2? What is the label that is having 2 as SIP sum? Okay, so what is the SIP sum? This is 0, this is 0, that as well. Okay, so what is the error in this code? Why the label sum I can do is, let's just check out the level sum. Shall we check out the level sum? While not q empty and nq size and current sum while not in minus minus 3 current q point. I think we are doing the level sum right. We are having the q and q size. I'm assigning index is equal to 1 because this would be the first level that we will be dealing with, and we will just pop the particular nodes, and so we have 4 and 9, so the sum becomes 13, and 13 minus the level sum, that is 13, would become 0, and similarly 13 minus 13 would become 0. I would increase 2, and again it goes into the loop q size, and it is I is equal to 1. Okay, so so we are reassigning the value I is equal to 1, so it just gets reinitialized. So if we check here, what is happening is 4 plus 9 13, and minus this 11, that is 2, and this is 13 minus 7, 13 minus 7, right? 13 minus 7, that is 6. Okay. So int I should not be assigned here because it will relaunch the value. We should be assigning I here. Okay. Okay, let's try to submit this. Don't know why my laptop is not charging. Okay, so there's this power cut, so that's why my laptop is not charging. So for the time complexity of this problem, in my earlier videos I have not discussed the time complexity. I have realized discussing the time complexity is also a part of solving problems. So that is something that I was missing. So this is a level dot traversal that will take order of n time, and then we are doing another level dot traversal, or we can say yes, this is a level order traversal again. So this will also take order of n time. So order of 2n would be the time complexity of this problem. And for the space complexity, we are using a queue, so it would be order of n, right? For there are n nodes in the particular tree, so the number of nodes would be n. You can just say the order of n space complexity and order of 2n time complexity. Now order of 2n as a time complexity, we can just round it up to order of n because 2 is constant, so it would become order of n, right? Okay. Now 54917 we're able to solve this particular problem. Now if we need to explain it to our interviewer, we can explain something like this. So I think we have explained it pretty well. But can we do this in a single pass? We have node 5, 4, 9, 1, 10, 7. For each parent node, I'm storing the level sum. For each parent node, I'm storing the level sum. No, for each level, I'm storing the level sum. And after that, I calculate the sibling sum, right? And then subtract that value, find the solution. Okay, good. But to solve it in a one pass, I will need to calculate the sibling sum and the level sum at once, not in two steps, but in a single step. I have to calculate. In this case, I am doing two traversal: one to calculate the level sum, the other traversal to calculate the sibling sum. If I am able to calculate the sibling sum and the level sum at the same time, then we can solve this particular problem in a single pass. But the issue arises that how we'll calculate the level sum in a single pass with the sibling sum, because when I'm standing at 4, I know that these two will be the child node, this particular 4. So the sibling sum is easy to calculate, but I don't know that 7 exists here because the 4 has only access to 1 and 10, and then 9 has the access to 7 node, right? So in my queue structure, even when I have 4 and 9, I can find the sum of these two. These are the sibling sum. Okay, I will find it, but I have to find the sibling sum of these two nodes at same time as a level sum. Then I can only do this in a single pass. Okay, how it would happen? How it would how it would happen? How we can find this in a single pass? Okay, so we are having a particular node. Let's try to draw a tree again and then think if we are able to solve in a single pass, then it's well and good. Or else we will shift to a second problem, and if there would be any single pass solution, I would work on it and then see. But let's try to do a single pass solution first from our own side. We have these nodes. Okay, I have these two children nodes and I have this node, right? Okay, when I'm standing at this particular node, I know that these two are my child node and these two are also the level sum of this structure. Okay, when I'm standing here, I have the level sum of this two as well as the sibling sum of these two. Okay, for the root node. But when I'm standing here, I only have the sibling sum of these two, but I don't have the level sum. But if I grab these two nodes, then I can have the level sum, right? I can have the level sum because I'm not talking about grabbing these two nodes together. After I pop this particular node and then pop this particular node, I can have the level sum of these two, these three nodes, but I won't be having the sibling sum. So for the sibling sum, I have to calculate the sibling sum some way. If I can store in a map relationship of the parent and child, then I can calculate the this in a single pass. But that would increase my memory complexity, right? Because I will be using a map also to store the relationship of the parent and child. Okay, so I would be storing the parent and child if in a map, then it would become difficult because we will be increasing the space complexity to decrease the time complexity. That is already pretty good. Order of 2n, we can round it up to order of n, and space complexity then would be increased. And I don't want that. Okay, so how can I have the sibling sum of these two nodes as well as the parent sum? Okay, if I hold on to these two nodes in temp 1 and temp 2, then I can have the sibling sum. I can have the temp 1 as my sibling sum, and similarly a temp 2 as the sibling sum, and the level sum would be find out already, and then I can subtract it. But the scenario that fails is that as we go deeper and deeper in our tree, the number of nodes would increase significantly. So this idea approach works good for when I'm dealing with these kind of two nodes only. But as soon as I go here, there are many sibling nodes. So how many sibling nodes I'm going to track? So that's become a issue. So solving it in a single pass is little difficult. It's just getting stuck here where I have to find the level sum, because if I find the level sum, then I will miss out on the sibling sum, and if I find the sibling sum, then I will miss out on the level sum. There should be a way to find the sibling sum and the level sum at the same time. There should be a way to find the sibling sum and the level sum at the same time. Okay, There should be a way to find the current sum and the level sum at the same time. I need to find the level sum and the current sum, sibling sum, sorry. I need to find the level sum minus sibling sum to calculate my answer. If I'm standing at this node, okay, let's just create a tree and again try to solve this. We have this tree structure. These two nodes are there, and these two nodes are there, and these two nodes are there, and there can be these nodes. I started to draw better with my mouse, somewhat better. Okay, so if I want to find the sibling sum of these two nodes, how can I find the sibling sum? I'm standing at this node. I can easily find the sibling sum, right? Right. And what about the level sum? Okay, so for the level sum, I will have my level vector, right? I will have my level vector, and when I'm standing at this node, these two sibling sum that I've found are added to the level sum here, and then this is popped out of the queue. And when this come here, it finds the sibling sum of its children, and it also adds its sum here. So now we have the updated level sum here of all the four nodes. So we can have the level sum, but still we are already popping this one out and this one out, right? What is the value of this node? What is the value of this node? Does not matter individually. We need to find the sibling sum of these two nodes and subtract the value with the level sum here that we have stored here. So we can store the level sum, right? If somehow I can just store the sibling sum also, so we can create a vector also for this and all the sibling sums. Okay, what if I find the sibling sum of these two nodes when I'm standing here? So there's a case when I'm standing here, I find the sibling sum of this and this, and instead of storing it in a vector, I store the sibling sum in this and this, and then add the sibling sum in this, my level sum traversal, right? Now these two nodes are storing what value? These are having the sibling sum. So if the sibling sum, this was 1 and this was, let's say, 10. So now these two nodes, both nodes are having 11 as the value, because that is the sibling sum of these two nodes. Just a second. Okay. Now that is the value of the sibling sum of these two nodes, right? Now the value is already added here. Only once with the value would be added, 11. Now when similar way, let's say it is 7 and it was 8. So now what is the sibling sum of these two? That is 15, right? So these two are storing 15. We have to store the sibling sum, so we can store the sibling sum at the node itself if we work this way. And this 15 is also added here, so it will become 15 plus 11, what, it's 26. So it would become 26. Now the value is 26. Now when I come down to this nodes, I will ask the level of this node. I know the level of this node. I know the level sum of this node already. I will subtract the value, and that it becomes 15. And now when I come to this node, it also asks the value, and I tell it the value is 15. Okay, so my laptop battery is getting down. So just a second. Let me just plug in the charger first. Much better, right? So where I left off. Okay, so now the value are 15 and 15 here. Now this has become 15, and it goes and finds a level sum, and it will become 11, and then again it goes and find the level sum, and it will become 11, right? So it would become 11 and it would become 15. Okay, so this is the level sum storage as well as the sibling sum together. So still, what, so for this particular question, if I have to write the code, then I have to go in advanced level for each node, right? So when I'm standing here, I would be storing, if this is I will add the sum at I plus 1 level. And when I am standing at I plus 1 level, I will just fetch the sum at I plus 1 level. So let's not make it that confusing. So what I can do is, let's reset this code. Let's try to let's try to solve this. Why? Just okay. Let's again create a queue. U queue. We have tree node. Okay, we have tree node, and let's name this queue, and this queue dot push my root node. Okay, so initially I am standing here, right? This is my root node. Initially I am standing here, and we already know that root val is 0. There is no point to working with that. Okay, good thing. Now what I need to do is do level order traversal while not queue dot empty int n is equal to queue dot size, and for each level I need to do the sum, right? So int cur sum, let's say, is equal to 0, and while n minus minus. Now my queue is having this node. I need to pop this node, right? Free node current is equal to queue dot front, and then this queue dot pop. So now currently I have the root, right? Now what I need to do is, now what I need to do is sum the left and the right of this node and replace them with the left val and the right val. What is this? What is this? Okay, sir. Yes. So currently I am standing. Currently, okay. Yes. Currently I am standing here. I want to find the sum of these two nodes, right? So I need to store the sum in some sibling value. So while n minus minus with this. Okay. Save the sib sum here, right? And sib sum. So what is the use of current sum if we are storing this sib sum? I mean to say, in my earlier code I was using current sum to store the sibling sum, right? That was the current sum. And the current sum should be added to, okay, so first let's add it to the current sum. Current sum is equal to. Now if my current dash left is not equal to null, if my current dash left is not equal to null, then value would become the current left dash val, else it would become 0. Now current sum plus equal to current dash right not equal to null, right? If not so, then current right dash val else 0, right? Now what I need to do is that I am having the current sum. So I'm having the current sum. I will add this current sum at where? So I have not created the vector to store the level sum, right? So let's create a vector int level sum. Okay, we have a vector int level sum, and what index I need to access. So when I'm standing at I need I plus 1, right? So in a level sum index I plus 1 plus is equal to current sum. So I add the sibling sum to the level of the sibling. Okay, so I add this to the level of the sibling. Now if current left is there, then what current dash left dash val would become current sum, and we will do the same for the right. If current dash right is, then do it, current dash right dash val dash current sum. Okay, now I have this current sum, I have added this to this. Good. Now the particular fact is, this is the logic that I have written for all the particular this till this node. Okay, but what I am missing is this. To say what I am missing is, so far I have the code the code is pretty right, but I'm missing the fact that I will need to replace this value. I need to replace this value with their level sum, right? I'm subtracting the level sum. Okay, so where would I subtract the level sum? I missed that particular part. When I'm standing at this node, I should subtract the level sum of these two nodes, right? Mm, so at this particular moment, I won't subtract the sum. Okay, when I come here, when I pop it for the first time, so initially, let's say the sibling sum here is 4 and 9 become 13. So I have stored 13 here and 13 here so far. Now these two are in my queue. Now when I come to this 4, I pop this 13 out, and I need to subtract that 13. I need to subtract that 13, that is my current value. The current val would become 13 minus the current level that I am standing, that is level I. So what I was missing is, need to do that also. So this was all good logic and everything. What I also need to do is reassign the current valve, that is current valve, because the current is popped out of the queue doesn't mean it can't be changed. The current valve will become its we can say absolute of level sum of index I, because I have already assigned it. So level sum of index I minus current dash var. So for when I'm at 4, its value was already assigned by 5. It already dealt with it, but I would say we had already dealt with this. Okay, so the current val would become dot val. Every time I come out of the loop, I will increase I plus plus. Okay, so I need to assign I also that I is equal to 1, because so when I at I is equal to 0, I think because I'm standing here and I have started the sum here from here at I is equal to 0. So if I has become 0, and I think I should level sum at I is already root dash val. So what will happen is that I was pre-assigning this, so I won't need to pre-assign this. Now what will happen is that at index 0, the I have already pushed. Let's draw this and work with the code. Okay, so we have nodes this, this, these two nodes, and this node. So I created a vector level sum. This is my level sum vector. Okay, sometime this mouse. Okay, just a second. We have a level sum vector for us, and we also have a queue. So initially in my queue I push my root and also push the sum, that is 5. Now for my queue and my root the value as pushed, I take the current sum as 0 because there is no sum currently. I pop this node out of the queue, that is the value of 5 has been popped out the queue. Now my current hold this is my current currently, and what I will do is that I will pick out its sibling, that are these two nodes, and I will add this to my SIP sum or the current sum whatever, and I will add these two value to my SIP sum, and then at I plus 1, that is this node, I will add the SIP sum value. So the SIP sum value is 13, so 13 values here added. This is my queue, not my vector, so the vector is here, and here I need to have a queue here. So this is my queue, this is my vector. Okay, so now I have 4 and 9 in my queue, and also the sum of them is 13 that I've already pushed. Now the current val, that was this 5, I will change it with the level sum. Level sum is I because I have pushed at I plus 1, so my level sum is still here. We'll just pick it. Level sum I, subtract with that the current value, so it becomes 0. So the value of 0 is assigned here. Okay, now when I come down to 4, in the similar way, I have come down to 4, the current sum was reassigned to 0, the loop was over, the current sum was reassigned to 0, and I come to 4, and at 4 I will add the children node value, that is 1 and 10, and after adding the value in my queue I will push the 1 and 10, and I pop this out, push 1 and 10. Now for 4, the current sum, okay, so for 4, the current val is 13, and the level sum is also 13, and the value would be subtracted with 13 and 13, so it would become 0 and assigned to the value. And similarly for 9, and the sum of this 1 and 10, 11 has been already added to the level sum, and the value has also been replaced to the level sum, that is 11 here and 11 here. So nodes are having the value 11 currently here, and now for 9 there is 7 the child. So 7 as a child, I add the value here, so it becomes 18, and the value of 9 has to be popped out of the queue, and the sum was 13, and 13 minus 30 would lead to 0. And the other node, that was the level sum, that was 7 because sibling sum, because it's a 7 node already. Now similar way, when I come to this, it will subtract with this and replace the value 7, it would come to this. So according to me, this code should work. Return root. It is a lengthy and little complex code than the last code that I did. But let's try whether it works or not. Let's see if it works. Okay, there's compilation error. Vector int level sum. What happened? Okay, there's spelling issue. Level sum. Level sum. Okay, absolute of. Okay. Okay, it works, should work, it should work, it should work, it should work. Okay, runtime error. Why there's this runtime error? Hmm, what is the runtime error thing? I know the runtime error cause. The runtime error cause is nothing else as when I come down to this 7, I try to push at I plus 1, but current sum value will become 0 and 0, and there is this issue because at this level, when I am at this level, I am pushing at level sum I plus 1, but there is no point of pushing that, right? Because it will cause an error. I'm trying to access. So I think I should add a case where if current left or current right exists, even a single node exists, then do this. Else don't do this. Let's try this. It still fails. Then I have to still getting that error. Uh, what I'm doing wrong, yeah. Current val is equal to current left val equal to current sum. Okay, good. The current right val is equal to current sum. That is also good. Why we are getting the runtime error? I consider the runtime error reference binding to null pointer to type int. Reference binding null pointer to type int. Okay, so I'm accessing null pointer somewhere. I'm trying to bind it. If current left exists, then only assign the value current val is equal to. So let's say if current. Okay, let's say if current, then only do this. Let's try this in Francis. If still doesn't work, I will have to do ChatGPT honest. Still the runtime error. Reference binding. There is the error. Into null pointer. Type int. Where I messed this code. I create a queue. Take the level sum. Left sum is equal to. If there is no root, then what? If there is no root node, then what? So if I have root, If not root, not root, return root already. Just a simple check that I have done. Work. Still the error persists. Okay. Not root q tree node q. I push my vector and level sum. Okay. I have my level sum. As my level sum, I push a task root bar. Okay. Well and good. Take q size. Current sum is zero. Tree node q dot current. Current sum is zero. Tree node q dot current sum. Current left exists. Does not exist. Zero. Left is not equal to null. Then add if current left is not equal to null, then the value of current val is zero. And if the current val, okay, it's good. Level sum I plus one is current sum. Okay, if current left exists, where I have pushed the current left. Okay. There's no pushing happening. Okay, that's the issue. Q dot push current left and q dot push current right. Okay, so if current right exists, then q dot push current right. And if current left exists, then q dot push current left. And let's try to do this. Let's see whether it works this time. Still, the runtime error continues. Okay. I was not pushing in the queue. That was not an issue. Okay, did I pop it out of the queue? Yes, I popped it out of the queue. Then what is the issue, man? What is the issue? Current val do absolute of level sum I minus current val. That's good. Level sum I minus. What is the issue in this code? Hmm, current right. Okay. Hmm, let's see. Okay. CM current dash left dash val. See out the right. Let's try to run this. Let's see what happens. Anything on the output. While not QMT, while n minus minus, current sum is zero. What is the issue, man? What is the issue? Line 1122 runtime reference binding to null pointer of type int. What is this issue? Tree node Q. Hmm. Okay, I think I've spent enough time on the runtime error. Time to do ChatGPT. Okay, let's see why it's giving. Why it is giving runtime error. Because level sum I is equal to root val. This binary code level sum is an empty vector, so accessing. Okay, level sum is an empty vector, so you should say level sum 0. some. Okay, say label label sum dot push back a root val. Push label sum push back the root val. And at this particular moment, let's try this. I might get some error, but let's see. Still the error continues. As a good one. Try to let's do this. Okay, the error continues. Okay, I don't just can't access it like this. Say ChatGPT, what should I do? Corrected C++ version, SQ. I can't just calculate the level sum of each children. Okay, I get it. So this idea is not working that well because we can't just access a vector like this. I can create a large vector and level sum. I can just say how many nodes are in the queue, right? Need to calculate the tree size for that and just create a okay. Let's see. Let's just revert it back a little. Okay, so I will just create try. Let's see what happens. Still the runtime errors persists. Out. So many errors. This okay. Let's try to submit this. This will probably fail due to the large amount of the nodes we have because 10 to the power 5 nodes and I am not working till that. Okay, it works. Okay, it works. So this was all the shit that was happening here. Sorry for the bad word usage, but it works well. Okay, it's a single pass solution and it worked. Had to use ChatGPT, but when you did use the solution of ChatGPT, so I don't think that counts. Yes, I definitely had to use it to find out where the runtime error was occurring. I'm really not good at with the runtime errors. Need to work with these kind of things also. I need to work on runtime error shit. Okay, so one problem we were able to solve in a single pass. So the updated time complexity of this problem is the okay, where's the comment? The updated time complexity of this problem is order of n. Okay, now we can solve this particular problem in just order of n. Now, moving forward, okay, I have to move forward to this problem. I've solved this one problem down, many left. Okay. Oh, my eyes. So yeah, guys, this is the third day. of this lead code problem solving journey. So far, I've seen countless rejections every day in my mail. And the worst part about this applying part is dealing with the workday. I mean to say, if you are in someone who is looking for job and you have to fill the workday form every day, you have to create a sign up, then do a sign in, and then you have to verify yourself in the email, and then the workday does not even works well with the resume. I mean to say, how well your resume is written, even how great your resume is, workday can't parse the resume. It passed the resume so crap that you have to copy paste each of the value from your resume, and if the values are parsed, they are in the wrong fields. I mean to say, why are you copy pasting my company name at the particular job title when they are separated and in separate columns? Why are you copy pasting my job details in that particular column, or mixing up my job details in the particular columns? For one column you are able to read my job details, right? And then for the same next column with the same font, you are just messing this up. And to say that is horrendous. That just feels, you have to fill that particular form, then you have to choose the language in which you can talk and fill all the details. I mean to say, and after that all this, you just get a rejection. I really like the greenhouse way of filling the job application. It's just simple. It passes the resume well. It doesn't ask for a lot of details. Just have to fill out the form and it works out. In Workday, it's hell. It's hell in Workday. You have to fill the details so much, and after that, you just get a automated reply that your form has been submitted. And after a week or two, you get a rejection. So it's a hell. Even after getting a referral, the thing is kind of same. I'm going to say, my luck has been so bad that you can't even describe it. I was able to get a referral to Amazon, and after that I gave the online assessment. The problem were not that particularly difficult. They were on easy level. Two DP problem. One was a partition DP, and one was not DP. One was a simple array problem, and was DP problem. Two problems, and then you have to give their aptitude kind of thing, that how will you be with the company and these kind of things, and all of this. And after this, Amazon does not replies. It has been more than 2 weeks since Amazon has not replied to my OA submission. I mean to say, if you want to reject me, reject me. If you want to select me, just keep the process continued. I mean to say, what is this particular part of ghosting the particular employee? I mean to say, I also have work. I have to also kind of apply at particular places and do these kind of things, and I don't know whether I will get a reply from you or not. If you don't want to select me, don't select me. At least give a reply, man. And there are these people. Okay, so it's just hell right now. Okay, so moving from hell, let's now focus on the problem. Enough of crying and acting like a bitch. Let's move to this. Delete node and return forest. Given the root of a binary tree, each node in the tree has distinct value. After deleting all the nodes, a value to delete, we are left with a forest, a disjoint union of trees. Return the root of the tree in the remaining forest. You may return the result in any order. Okay, I am given the root of a binary tree. Each node in the tree has distinct values. After deleting all nodes, the value to delete, we are left with forest, a disjoint union of trees. Return the root of the tree in the remaining forest. You may return the result in any order. Okay, so I have these nodes, and there are these two delete values. The values are 3 and 5. And when I delete 3, the tree would become null here, but the 6 and 7 are still there, and I am pushing them in my solution array as separate tree nodes or separate root of trees, that these are new trees. If you work with DSU, you will know that this, it's kind of breaking it into components, right? What we are trying to do, okay, what we are trying to do is this tree. Okay, let's get this done. Okay, where's the Okay, it also has two bits, right? Okay, this has also two bits. Now when I have to delete this node breaks. So now we have this node anymore, and these two, now since it was having, these two were having a common parent, like a DSU have this is the common parent, but now the parent is deleted, so these two are their parent itself. So their parent component was deleted, so they become their themselves. Okay, so for this, how shall I approach you? Okay, I have here, I have here, also have here, so I have here. Now when I'm standing here and my parent was deleted, I become a separate node. I become a loner, right? Loner, and loner can't exist. So they need to find a room so they get into array. And since the order does not matter, so loner can be pushed in anyway, right? So I start from my root, I go left, and then I go right. At left, I check if there's order to kill me, then please kill me but spare my children. So take my children, push them in the array, push them in the array, but kill me. Okay, good. But let's see, we have 1, 2, 3, and 5. Okay, these are test cases here. Case 2, right? This. Why this? We have 1, 2, 4, 3. What are the nodes to delete? The node 3 only, right? So it would become 1 to 4. It's pretty easy case. But let's consider one, two or more cases. What if I have to delete the root node still? So this is the parent node and this is the child node. This is the child node, this is the child node. And I have this time to delete this node and this node. I want to delete all these three nodes in the tree. I come to this, I ask, are they my child? Yes, they are my child. Am I to be deleted? Yes, I am to be deleted. So please delete me, but don't kill my child and push them in answer. Okay, good. I push these two nodes in the answer, but there comes an issue. What? My child was also to be killed. My child was also to be killed. Okay, so since my child was also to be killed, what I need to do is now pop this child out of the tree, out of the array where I was storing this solution, and I have to pop my child out. And but since I am also having kids, so please push my kids in the answer, but please pop me out. Okay, and when I come here again, I am again in the array. Since I was to be killed, please pop me out of the array. Now storing it in the array is a easy solution, but popping it out of the array is difficult. I have to keep a track of index. Just like previous solution, if I make a 1000 big array and then I keep a track of, I push this particular tree at this particular index, and when I need to pop it, just pop this particular index. But I have to, since I have to pop this, I have to left shift all the particular solution. And let's see how many nodes we have. The number of nodes in the given tree is at most 1000. So if there are 1000 nodes, and for if I have to delete 500 nodes, let's say, on the right side, so I do 500 shifts every time. And so what is the particular way of this problem solving? Just a second, guys. My dog is kind of causing a issue right now. So just a second. Okay. Now for each solution, Now I have to do 500 shifts, 500 pop outs. So I do plus 500 insertions, and then I do 500 pops, and then again 500 shifts for this particular way. And one shift will not just be ending here, it would be take, let's say there are n elements to it, n elements to the right of it, so I just shift it to the n elements, I have to shift n elements more to the left side, so it would become a mess of a solution. And especially I have to deal with this popping and shifting particular part, this will become a more complex, so this is not going to work. Now for this popping and shifting, if I create a map, then I can do it in a smaller time, because for every node, what I will do is I will just find that if this particular tree node exists in the map, and if it's true, then just erase the value from the map. I can just have a map. Instead of storing it in an array, I will store in a map. I am here. I ask if I am to be deleted. Yes, I am to be deleted. Plus, but please don't kill my child. So my child are pushed in the map, and the value are marked with true. Now, when I come to my child, am I to be deleted? Yes, I am to be deleted. Am I present in the map? Yes, I am present in the map. So please don't kill my child. Push them in the map, but please erase me from the map. Okay. And then we can do the same operation for every particular node. But now what I need to do is I have to create a map, and for that map I have to push and delete from this map. Okay, that is good and much better from my last solution. And then finally, when I have pushed and pop all these particular nodes and done through this, I can just go and push all the nodes from the map into my answer. Okay, that is one way of solving this problem. Can there be a better way to solve this problem? Because this map operation will also be costly to us, not like it won't cost to us. So what I'm doing, if I go this way, right, I'm going from top to bottom, going from top to bottom while deleting. But what if I go from bottom to top to delete? Now what I want is, instead of going from top to bottom while deleting, I'm deleting this node, then asking whether my child exists or not, and then I delete this node and ask whether my child exists or not. If I go from bottom to up, to say I first reach here, I ask if I am to be deleted. Yes. Does my left and right exist? No. Just delete me. Okay. Well and good. This node is deleted. This, let's just pick a color. This, I am deleted. Okay. Am I to be deleted? No. Let's reach back. Am I to be deleted? Yes. Then delete me. But before you are deleting me, does my children exist? Yes, my children exist. So push it in the answer. Since it already has been checked whether I exist, my children has to be deleted or not. So the solution will work, because since my children was not to be deleted, it would be easy. Or I don't need to check whether it has to be deleted or not. Now I come back to my parent, it has already checked on the left side whether to be deleted or not. Now it will see what I need to do, and it will just delete itself and push these children in the answer. So it might be a sound little confusing, so I will just draw a tree again. Okay, I'm using a circle this time. Okay, well this time it looks good. I can just use a circle, better, right? Just use more circles. Control C and Control V, and then okay, so this much is good. Now I can just connect these. Okay, I am standing at this node. I ask, am I to be deleted? If yes, then delete me. Okay. And check before deleting. Before deleting, please check if I have children. If yes, then please spare them and store them. Okay. Since we are going from down to up, there would be no nodes for the leave node. There would be no children for the leave node, so it would be deleted. Now this would return null to its parent. Since it was deleted, it would return null. This node was not to be deleted, so it returned back to the parent. But this parent node was to be deleted, so it will ask, is there my children? It would say yes, there is one children that is on the right side. So since there is a children on the right side, please store it in the array and don't kill him. Okay, so I store this right node in my array, separate node. This is the right node. I will store it in my array and delete me, and I will send the null. Now similar way, I have reached the top, and just the call does not just exit ends here, because the left call ends and then the right call goes. So firstly the right call goes, and I ask the question, am I to be deleted? It says no, I don't have to delete you. So it goes back that I don't have to be deleted. Now this node was to be deleted, is asked, is there my children exist? Yes, my one children exists, so please don't kill him, store him in the array, and please delete me. So this node was also deleted. So it becomes a simple recursion problem, right? Now let's try to implement this. So I will take a void type class in this, oh sorry, void type function, because I don't think I have to return anything, just need to delete, right? Or I need to return the root. Okay, what I have to do is, do I have to need to return the root, or I have to, well, I have to return the root, right? After deleting I return null, and if I don't delete, if I don't delete, then it doesn't become null. Okay, so what should I do? Should I return? Let's just start with void, and if we need to return, we will check. Okay, so let's call it void solve, and I will pass a tree node, that is my root, and two deleted array. So to access fast, let's just use unordered set. UNORDERED set, that will have what tree nodes. We have to delete value or nodes. To delete is value. So sorry. We will have another set that will store this, and just call it st, right? And do I need anything more? No, I don't think I need anything more apart from this. What I need to do now is, if not root, then just return, and call the recursion. So I'm at root left. I will ask to solve my root left, comma st, and root right solve root right, comma st, right? Now these nodes are to delete and check that particular thing. Okay, good. Now I have reached at the last node, or I have returned the fall, because that was a leave node. Now if st dot find root dash val is not equal to st dot end into I was able to find the value in the tree, then I need to push it in an answer. So let's just create another vector int, call it result, and result dot push back root left. But this would only happen if root left exists. So if root left is there, then result dot push back root dash left, right? Okay, so are we returning the values? We need to return the root of the new tree, right? So it won't be holding the values, integer values, holding the tree node. So I will push the root left. Okay, if root right is there, then result dot push back root right. Okay, good. And after I have done this, I just need to return. I'm not pushing the current val in this, but there is an issue. What is the issue? That if I am at SA, if I am at this, just let me this no way this. Okay, it's going back just a little more. Oh, okay, this much is enough. So if I needed to delete this node, let's say I have to delete this node for this. If I have to delete this node, I have pushed the value of the left child, I have pushed the value of right child in my answer. I have pushed the nodes in my answer. But if I return from here only, then I have not deleted this. And when I have to delete this node for the case, I have to delete this node. I will see that the left child is still like this. So I will miss the case. So I just root is equal to null. Ah, instead of this, why not just convert this into a tree? Then I can just return null properly, right? Why take any tree node? Solve. So I will just return null here. Since this case broke here, I will return null because I don't need this node anymore. Okay, good. Now, if this cycle was able to be completed, then return the root. Or if the node was not to be deleted, then I would not need to push these two nodes. Then just return the root. Nothing would happen. Okay. Now I have to do here. I have a unordered set. ordered set ordered set. I have to do int. Sometimes I have quite a lot of confusion writing the unordered set, so that's an issue. Vector that will hold my tree nodes. Let's call it what I was calling this particular vector result, right? Let's call it result here. Now for auto auto x that will go in my to delete delete. I need to do is st dot insert. What I need to insert is the value x, right? I insert the value x in my st. Now what I need to do is just need to do is delete, right? So solve root comma st comma result and return result. That's my result array that I need to delete. Oh, no, that is holding my answer. Return is causing the return. What is the issue? Okay, so I'm just returning here. It should return null here. Okay, it should return null because there is nothing. So it's compilation error. Root left is just calling st. I need to call the result also. I need to call the result also here. Let's just call it the result also. Result also. Let's see whether it works. Again, the compilation error. What is the compilation error? Okay, without comma. Wrong answer, wrong answer. Why? I am pushing 6 and 7, but I am not pushing my root. Okay, in this case also, there was nothing to delete. So I'm missing out on my root. Why I'm missing out on my root? To say I start from my. Okay, just a second. Okay, I start from here. I check whether the left or right does not exist. I delete this node. I do the same here. It is not to be deleted, so the value of this root is to be returned here. Okay, good. When I come here, it has to be deleted. It is pushed in the array. Good. Now this returns null to its parent, but this returns a value or root r right. That I am the r right node of the particular tree. So I'm r right. Now this is r right, but this is nothing. So this node, let's say, was not to be deleted, so it will just return the root. It will just return the root. So I just get this remaining tree as my answer. But what happened is that I did not push this particular tree in my answer itself. So that's why I was missing on the my parent part. So since I was missing on my parent part, what I can do is, if st dot find root dash val is equal to did I find it? No, it's just st dot end. The whole st was traversed and I was still not able to find that value in my st. Then result dot push back my root also. What happened? The what the hell? What is the issue, man? What is the issue? Error expected. This is the error. Well, that's why I was saying why I'm getting error. Mm. So, to run it, please run. Okay, it run. Let's try to submit this. Okay, so it worked. Now let's try to remove this history part. I was just checking it for the case whether it goes well or not. Now let's try to run this. I mean to say, if the root existed, then it was not to be deleted. And just try to submit it. It is not like, okay, wrong answer. Huh? To delete 2 and 1. But when I reach to this node, I should have realized that I have to delete this. I'll push my child here and I will just delete this node. So it will return null, right? It will return null. It could return null, but the particular fact is you have returned null here. That's not the issue. The issue is that you returning null, but it does not erase it. Either you set this value to null, you just return null. You didn't delete or do anything special to this. You just create it, push the remaining tree. You did not delete it, so you just need to check it. So the original idea was good to check it. You have to be cautious these kind of problems. Okay, so I was able to get through this also. Okay, let's discuss the time complexity of this problem. We are traversing each of the node once, so it would be order of n the number of nodes in the tree. And what is the space complexity? We are using a set, so order of set, so we will push, and we are okay, so order of n would be the space complexity. We could have a case where we have to delete every node of the tree, so yes, we can have order of n. Time complexity order of n, space complexity order of n. Nothing better than that. Can there be a better solution than that? Let's see, deleting a node of root tree. I go every node, I delete it. My solution, I go to every node, I ask it, are you to be deleted? And if yes, does your children, do you have children? If yes, then let me take them to a safe place. But after I've taken them to a safe place, I will just delete you and move back to your parent and ask the same question. There is no magic way in which I will know that these nodes are to be deleted and these nodes are having these children and just push them in the. I can store them in a map that would just. I will need a extra loop for that particular thing. I will need a extra loop for that, and what I will be doing is then I will be then again going from top to bottom instead of going to bottom to top like I went in my recursion solution. So I don't think there's a better solution. It's just taking out of n. I don't think there's something that can go out of log n or something like that in this particular problem. So yes, this is the best solution that I can think. It is going in a single pass. It's not like I'm doing two pass or three pass like my previous problem. That there I was doing two pass, and then from that two pass we can go to single pass. But yeah, so we were able to do two problems so far. Let's do our third problem, that is flatten binary tree to linked list. Okay, enough of this sketching. Just remove you. Should I go with all these problems today, or should I just stop with one more problem? That's quite a thing. I've been recording for quite long. I think the video has already become at least 1 hour long because it's 11:30 in my clock, and I started somewhere around 10. So 1.3 hour, 1.3, 1.30, 1 hour 30 minutes are gone already, and then I have to fill all these job applications that are here, and then I have to beg for referrals on different kind of platforms. It's a long part. I'm thinking of doing. Okay, this is a max product problem, and this is a flat end. So let's do these two problems, and then we will end for today, and then we have how many, five problems more, right? Apart from these five problems, if I get time to solve these five problems today on video, tomorrow on video, not today, tomorrow on video, because there's only 1 hour, so there's no today and tomorrow left. But if I get time to solve these five problems, because what happened was that I'm recording this video on Thursday. I was supposed to record this video on Wednesday and post this video on Thursday. But what actually happened was, on Wednesday, I had a lot of work from my internship. I had to make the 3 to 4 web pages, front end pages, and I have to adjust the code for that. And when I adjusted the code, it took me around 10. And after 10, when I just tried to take a nap on my bed, and after just taking a nap, I realized it was 3, And then I realized that I've already passed my limit and I won't be able to record a video now at 3. So then I decided that I will record the video in the morning and post it in the morning. So then in the morning there was this rain, so there was this power cut and all. So yeah, so I was not able to record the video in the morning also, and I was also doing the job work. So now it was not able to do it in the morning. So I'm recording it in the night, and I would be publishing it in the night also. So just as soon as I complete it, I would be publishing it. Guys, if you have any job referral or anything, just comment in at, or just comment me. I'm also thinking of starting a GitHub repo, and in my GitHub repo, I would push all these solution and all the approaches and push my YouTube link. Let's see where it takes me. Let's just solve this particular problem, and then we'll move to the next particular discussion part. And just have to talk too much. Don't know why. I have to continuously speak. Flatten binary tree to linked list. Okay. Given the root of a binary tree, flatten the tree into a linked list. The linked list should use the same tree node class where the right child pointer point to the next node in the list and the left child pointer is always null. Okay, the linked list should be in the same order as pre-order traversal of the binary tree. Okay. Hmm. Given the root of a binary tree, flatten the tree into linked list. The linked list should use the same tree class where the right child pointer to the next node in the list points to the next node in the list and left child pointer is always null. 1, 2, 5, 3, 4, 6. Okay, let's draw this. We'll use circle. 1, Control C, Control V, Control V, Control V, Control V, and how many nodes it was having? There's one more node, right? So give me a Control V. Okay, that's good enough. Now when I'm here, I'm here, and I'm here. What are the nodes? It's 1, 2, 5, 3, 4, 6. 1, pretty great. 1, 1, 2, 5, and this is 3, this is 4, and this is 6. And then I convert it into a linked list or whatever it says. 1, it's 2, it's 3, it's 4, it's 5, and then it's 6, right? I just have to 1, 2, 3, then it's 4, it's 5, and then it's 6 here. Okay, good. I convert this tree into this linked list of a pre-order traversal. The linked list should be the same as pre-order traversal. Okay, so what is a pre-order traversal? We go to the root and the left of the root and then the left of the root, and then we go right, and then we go to the root back and we go to the right, and there is no left, so we won't go left. If there existed a left, we would have gone to the left first, but there does not exist any left, so right. Okay, so and then that's the tree. Okay, we have the pre-order traversal. Now if you look closely in this tree, what we are doing is making the left side null and taking the left side nodes and attaching them to the right side nodes. Okay, I have 5 and 6. I have to attach these 5 and 6 to my 4, right? I have to attach these nodes to my 4. So if I attach these nodes to my 4, it would look like 1, this 2, this 3, and somehow let's say by some magic I was able to attach these 5 and 6 here, and now I don't have anything here. And then after attaching my 5 and 6, I will just go here and attach this 2 to here to my 1, and then all the values of the 2 are already here, and I will make this null. So now it's 1 and this is null, and then this 2, all this 2, 3, and this 4, 5, and then this is 6. So now there's this null, and this is 1, 2, 3, 4, 5, 6. Now this 3 needs to be deselected here. A null should replace this 3, and this 4, 5, 6, just like the last time I picked 5 and 6 and connected it to the left node of my current root node. I connected to the rightmost node of my left node, right? And to say if there was something like this 4 here in the scale, let's say there was this 4 attached to this 3 and not here, and there was this 5 and then there was 6 and 7, it could have worked out. So I connect this 4, 5, 6 here because there was no right node to this 3, right? So how come I can go here and then I take this node and I attach it here? If I attach it here to my 1, then where will I put my 5 and 6? I need to put it at here at 4. To reach this 4, if I ask the left node of my root node that, hey root, do you have any right child? If yes, then please go there. And then again that right child I again ask, hey right child, do you have any other right child? And if say yes, then go there. Until and unless they are no for the right child, if I connect this 5 and 6 to that right child, it would become a tree. It would become a structure that I like. And then I take this 2 and connect it here. This connection was already cut. Since 5 and 6 was connected to this 4, this connection was cut. Now this is a new right. But the issue is that I have a new right. I have this 1, this 2, but to this 2, this is still 3 connected, and there's this 4, and then there's this 5, and then there's this 6. So now from my root, I go to my root right, and the root right then again goes to its left and asks, hey left, do you have any right? And the left says, no, I don't have any right. So the node says, since don't have any right, just take my right nodes and connect it to your right. They will become your right, and you please remove yourself from my left and become my right. Okay, this could be happening. This is recursion. This could be happening, but I will need to go to the left and to the right and to check this. Okay, to check this, I have to write it. So if I write a void type, that will allow me to the rightmost node, but there is no point of writing it as a void type because there is no such thing. I have to return it right now. So free node return, let's just name it return right. The name of this particular function is return right. It will it will ask this node to give me the most right node that it has. Free node star, if not root, return null. Okay, else what will happen is, if root dash right is there, root is equal to root dash right, and after that when I finally then return root. Okay, if there's no further node, then just return right. uh, Why would we return null? I mean to say, while I have just it's just a like a linked list code, right? You have to just a linked list code. While I have right, just go till right, extreme right as US you can go. While I have root right, so it's like let's take a tree where I have a big right. This. So I come here. I say, do you have a root right? Then go there. Do you have a root right? Then go there. Do you have a root right? Then go there. Do you have a root right? Then go there. If you don't have a root right, just quit it and just return me the root. Okay, so I will return. This is my rightmost node. Okay, there was no point of this return null and all this. Okay, so what I need to do now is go to the left of my root node. Okay, so first thing first is that I have to go to the left of my root node. So I have to take the root, right? While I have root, only then I would able to traverse this tree. No? If I don't have root, then what is the point? Just like this particular code. If I don't have the root anymore, then there will be no left, and if there is no left, then just return the root. If root has a left, then do what? Then I will need to store it in a tree node. Tree node. Let's say temp. Temp will called return right. That would take my root left. Now from the root left, this was a node, and this has sent this particular root left to solve get the rightmost node. Now the temp would return me the rightmost node. I mean to say the temp would return me this node, this last node. Now the temp has returned me the last node. What I will do is this temp right would be changing. Okay, sorry. The temp right would be changing and would become root right. Whatever was whatever was here, whatever was here, just pick it and just connect it to the rightmost node on the particular side. Okay, good. Now what about the left? Now the left node is still there. I have the root left. Now what will happen is that root right that has already been connected to the temp is to be changed and it has to become root left. Okay. What about root left? It will become root left will become null. There is nothing left for it. Has become into a stale node, boring node, useless node. Okay. Now what I need to do? If root left, then this would happen. Okay. Now root is equal to root dash left because sorry, not root dash left as root right because now since I have connected this node here, I had this node, this, and then there's this, and there was this node. I have connected this node to this. So what has become it's this, and this node was already connected to this, and this was already connected to this. But I don't know whether it has more node or not. So I will just go to the right. Okay, go to the root right. It's a void test, so there's nothing to return. Let's try to run. Let's try to submit this. Okay, so yeah, we were able to do this. It also has a order of n time complexity, not more than that, not less than that. Okay, so I don't think there's any better solution than order of n time complexity for tree problem. I don't think that tree problems go less than order of n. The rare case where you might be implementing some binary search. Even if you have to implement binary search on a tree, You have to do in order traversal. That will take order of head time. You can go order of h to find the height of a tree, maximum height of a tree or anything. That would take order of h because that's the maximum height of the tree. But apart from that, I don't think there's any better solution than order of n. There might be cases, there might exist a better solution that I have not seen so far. I've never worked on that. Okay, now now I think how long has the video been running? Oh no, there's no timestamp in this thing. Maximum product of a splitted binary tree. Okay, so I need to find the maximum product of a splitted binary tree. Given the root of a binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sum of the subtree is maximized. Return the maximum product of the sum of the two subtrees. Since the answer may be too long, return the modulo 10 to the power 9 plus 7. Note that you need to maximize the answer before taking the mod and not after taking it. Okay. Okay, this looks interesting. Now my throat is so bad currently. I can't even describe it. Let's see what we have. We have 1, 2, 3, 4, 5, 6. Okay, we have 1, 2, 3, and 4, 5, 6. Let's draw this. We have let me draw this using one, and then just let me copy this. 2, 3, 4, 5, then 6, right? Like this. Okay, the six is here. Okay, good. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and then a 6. Okay, great. What is the solution for this particular problem? We split the tree at this particular edge. The sum is 11 here. If I split my tree here, these have sum 2 plus 4 plus 5, that is 11. 11 sum here, 11 sum here, and 1 plus 3, 4, 4 plus 6, 10. They have sum 10. Now it would become 110 as my answer. Okay. Now what if I would split my tree here? Then it would have been 4 plus 5, 9, 9 plus 2, 11, 11 plus 1, 12. 12 into 9 is 108. So 108 is definitely smaller than 110. So it's not a better solution. So the split needs to maximize the both side where we are splitting so that the product becomes bigger. So as large as I can make the sum on both sides where I split, not just on one side. Into the side I am splitting, it should maximize the both side. It should maximize this side also and the other side also. So to do this, we will split into two sides only, not three sides. Given the root of binary, split the tree into two subtrees. Okay, so we need to split it into two trees, T1 and T2, let's say. Now I need to split the tree into T1 and T2. Whenever I make a split, okay, whenever I make a split T1 and T2, I will keep track of the value of T1 and T2. I was thinking of keeping track of T1 and T2, and whatever the maximum T1 and T2 we find, that would be my answer. But there is an issue. I can't just say that this T1 and T2 is good and this T1 and T2 is bad. I have to know their product. And eventually, if I have to know their product, there's no point of storing T1 and T2 separately because first I divide the particular tree in this particular way. Then I calculate its sum and store that T1 is this. and that T2 is this, and then I check what was the maximum T1 and T2, and there's no maximum T1 and T2, it's the maximum product. So this is not going to work. Okay, no problem. We have a tree, we have to split it into two parts and calculate what is the maximum product. So what is the total sum of the tree? Total sum would be the sum of all nodes. Okay. And if I split tree into two parts and their sum is T1 and T2 individually, then T1 plus T2 is equal to total sum, right? So T2 is nothing else as total sum minus T1, and then T2 is there. Now what I can do is calculate the total sum of the tree. Good. Now if I have to make a split here, then I will go from 2 2, and every node below 2 I will do a traversal and calculate the sum from that particular 2 to all the, from 2 there would be a new subtree, and I will calculate the sum of this subtree, subtract it and multiply it as, because the T2 would be already there from the total sum minus T1 sum that I would be getting from here. That would be my answer, right? So now the only issue that I have is T total sum can be calculated in one pass. Okay, that would be order of n, right? I have to visit every node in the tree, order of n. Now, from every node of the tree, I have to make a split because I don't know which split is the best. So I have to make a split. Let's just erase all these lines. Okay, just good. Okay, so from every node of the tree, or before every node of the tree, from every edge of the tree I have to make a split. So I will make a split here. Now this 2 and this sum is calculated. Okay, one traversal this. Again there are two edges from this 2. I will break for this 4. Okay, one traversal here. I will break for this 5, one traversal here. Now I will break for this 6, one traversal here. I will break for this 3, one traversal here. 1, 2, 3, 4, 5. 5 traversal for this tree only. Okay, right. 5 traversal these plus 1 traversal that I did. That was total sum traversal. So total 6 traversal for this tree. Okay. For 6 node I did 6 traversal. How many nodes can be there? 2 into 5 into 10 to power 4. Okay, so 2 into, from 2 to 5 into 10 to the power 4. Okay, okay, great. From 2 to 5 to 10 to the power 4. And if I have 5 to 10 to the power nodes, and I have to do 5 to 10 to the power 4 traversals. Not just 1 or 2 traversal, I have to do 5 to 10 to the power 4 traversal plus 1 traversal extra for the total sum. And these are the 5 to 10 to the power 4 nodes that are to be traversed. So we will make this traversal. So it is totally inefficient. It is a garbage approach, because if I am making 5 into 10 to power 4 traversal, that costs order of n, because we can just say there are n nodes below every subtree in the tree that I have. So it is for every n nodes in the tree we make order of n traversal, that is n square. So 5 into 10 to power 4 into 5 into 10 to power 4, you can just calculate the number how big it gets. The total garbage approach. So what could be better? If I can't make double traversals because of the time constraint and the memory constraint to store the sum, I mean to say I have to not memory constraint, but the sum that I would need to store would be also huge. So how can I do this? I have to do better than this. So what can I do? Let's we are going from top to bottom, right? Let's go from bottom to top this time. I am at node 4, and what if I break a node here? The sum would be 4, and the remaining total sum I don't know. Remaining total sum I don't know. For now I don't know sum, but I know there exists a node called 4, right? Similarly, if I break at 5, then the sum is 5. I don't know the total sum, but it exists somewhere. Similarly, if I break at 2, then 2 plus 4 plus 5 is 11, but I don't know the total sum, but it exists somewhere for me. Then again, I go at 6, I break at 6, I get 6, that they exist as 6, but I don't know total sum, but it exists somewhere, but not today right now. Now I come down to 3, come to 3, I break at 3, 3 plus 6 is 9, I don't know the total sum, but it exists somewhere. Now I am at 1, the sum is all these nodes, that is 4 plus 5 9, 9 plus 2 11, 11 plus 1 12, 12 plus 6 18, 18 21. Total sum is 21. Okay, if I have to calculate the total sum of the tree, I can go from bottom to up, right? I can go from top to down, and similarly I go from bottom to up, or even I can go from top to down, that really doesn't matter. If I go from bottom to up, then this 4 and this 5 will send their value to 2, and the value of the 2 will be added to these 4 and 5, and it will send its combined value to 1, that would be 11. And similarly 6 and 3 would send its combined value, that is 9, to this parent node, and then the parent would add 11 plus 1 plus 9. Okay, so that would become 21. And similar way, the node 3 would receive 6, and node 2 would receive 4 and 5, right? But if I am going from bottom to up, you can see one thing also, that I was able to find the sum 4. Okay, I was able to find sum 4 once. So one sum that was 4 of the breakage of the T1 and T2. So the T1 part, once this was calculated, I don't know the total sum yet, but I have the 4 once. So I can store this 4 in an array. So let's say I have an array called sum, and I will push 4 in that I had 4 once. Now I come to 5. Now 5 says, see, there is no left and right to me. I don't know the total sum right now, but I existed somewhere. So I was also a part of subsum, or the T1 part that you would calculate in future. Now we 4 and 5 pass their value to 2, and 2 adds its value to 4 and 5, it becomes 11. And so if I break here, the sum would have been 11. So the 2 says, see, I can become a subsum, and I would be 11. So the current sum, total sum does not exist yet, but it will exist somewhere in the future. So you can just store me that I am 11 and I existed in past. Okay, now let's go to 6. 6 will also do the same. It will say, if you break before me, then the subsum of the sum below, the sum just before breaking me would be 6, and I existed, and the total sum does not exist yet, but you can store me and use me in future. Now if I break before 3, it would say then 3 would say, from me to all the nodes below me, the sum is 9, and since there is no total sum yet, you just store me and you can use me in future, right? Now when I reach at 1, then I have the total sum, that is 21. Okay, and we won't store this sum as sum in the array, because we can't break before 1 or any place. So this one will be stored separately, it would be total sum, right? Okay, it is different, so it is total sum. Well, we can also store it, because the particular fact is that total sum is here, and if we anyway we break the tree anyway, and the total sum, if we try to break there, it would become 0. So there's no point of the product, that would become 0. So it won't affect it, but we can store only these sum in the array. Now what I need to do is, now when I come here, what I need to do is just traverse this array once. I will ask 9, hey 9, just subtract from 21 minus 9, and I will find the remaining sum of the array and multiply it with the 9, and we will find the product. And in the similar way, we can keep track of this. Now, this odd of n traversal for this plus odd of n traversal on this array that I will have, because it will have also not have n nodes, but we can say n, around n, not perfect n but around n. So yeah, so it will have a order time complexity of order of 2n, right? Order of 2n. It is not as complex as the last one where we are having n square as our solution, because we were doing traversal from each particular node. So we are not doing the same thing here, and the time complexity has reduced to order of 2n only. Now, what could have even better that if I could have total sum some way, but there is no way to have total sum in just once. I will need to do a traversal once on the tree. This, I have to do the traversal on the tree once, and then I can just do divide, subtract this, and particularly check this. Let's try to code this solution also. So what I need is a function that will return me what is the total sum. Okay, so int total sum is a function. Okay, it will take my tree node root, and what it will return, it will return the root val and nothing else. And what about storing an array? So let's create a vector int, let's name it as add for now. Have add. Okay, if not root, then return 0, then return 0. Okay, no problem. Now int left is equal to tot sum root left, comma add. Int right is equal to tot sum root dash right, comma add. Okay, good. Now I have got the left value plus my right value. So what I can do is add dot push back. What I will push back, left plus right plus root val. Okay, this is pushed in my answer. And apart from this, return left plus right plus root dash val. Okay, I have returned the value, and all this sum is stored in that array. A vector int app, and I call this int total sum is equal to tot sum from my root node. Okay, from my root node I have calculated the answer. Now what I need to do is for auto x array, and pass the array. For auto x on array, you just need to find the best answer, right? So int max answer is equal to int min, initiates in int. So max answer is max of max answer, comma, what is its total sum minus x. Okay, total sum, you just take it, and y is equal to total sum minus x. Okay, do what, x into y. in a bracket do x into y. So in a bracket what I will do is just do x into y. Okay, I have done x into y. What I need to do is now return max answer, right? Or is there anything left to do? Don't think there's anything left to do. Let's try to run this. See what happens. What is the issue? Okay, this is the issue. Okay, let's try to submit this. What is the runtime error? Okay, there has been an overflow. Okay, so just again run it. There's no point of again running it. Have to, what is the value? Say 10 to power 9, right? Let's just declare const mod is equal to, how we declare 1e9 plus 7. Okay, great. Now divide this with my mod. Now just try to run it. Good run. The running part is no issue. It was again. What is the issue? Okay, I'm not const in mod. Let's try to submit it now. It should work. Still, the overflow continues. The overflow is coming here, right? Let's do one thing. Just mod it also here. Uh, let's try to. Okay, again we have got the same error. Uh, let's just do it long instead of just long to avoid this overflow. Change it to long. Here also we'll do it long, and here also long long. Okay, sometimes it's just long. Everything is now long. Even I will just make this array also long. Just remove every chance of overflow. Delete this overflow particular thing. Now let's just see what happens. Okay, so I'm able to do this, but I think should I change it to also to long? Nah, I don't think it should change from long to anymore. I think it should work this time. Wrong answer. Man, why this so unexpected? Whew, just pathetic right now. How many cases? 32 out of 54. Huh? Okay, so I was just double dividing it. That was the issue. And how many summation it took me? Just four solution submissions to reach the final correct answer. So I think it's enough for today, guys, because the recording has become more than 2 hours. Let's just stop it. See you in the next video.